Hi everyone, welcome to our video on the Nernst equation and determining cell potentials at non-standard conditions. I just wanted to provide this for you in case you wanted some extra review on this topic. It tends to be perhaps the most complicated topic that we'll cover in the electrochemistry unit. So up to this point, we have learned that cell potentials, when they're positive, are spontaneous. So we know that if E cell is positive, that equals a spontaneous reaction. So essentially, if we set up a galvanic cell or a battery electrochemical reaction, and if we get a spontaneous reaction taking place, we'll observe a positive voltage. Of course, we also remember from our Chem 1B thermochemistry unit in our equilibrium unit earlier this quarter that if we have delta G equal to a negative value, that also equals a spontaneous reaction. So we might begin to think that we can relate delta G and E cell together. And so we have these two equations here where we can say that delta G at non-standard conditions equals minus NFE, which would be the cell potential at non-standard conditions. Or we could say that delta G naught equals this minus NFE naught, which would be our standard state. Which of course, if you remember, we have everything in 1 molar concentrations, or if we have gases, everything's at 1 atm. So you might be thinking, well, where does this relationship come from? Well, hopefully that looks somewhat like a linear relationship to you. And if we think about plotting delta G versus E cell, then we see that we have a negative slope. So we could say that this equation might have the form y equals mx plus b. Of course, we can see here that our y-intercept is 0 because there's no b term. And we know that if delta G is positive, E cell should be negative. So if we were to plot, we would probably start somewhere over here. And then we know that we have a negative slope, and that when we get to positive E cell values, we should have negative delta G. And so we could imagine that this relationship might look something like this. Of course, our y-intercept is 0, as we just mentioned. And we can see then that the slope of this line then just simply equals NF. So this number of moles that are in the reaction, and then of course this Faraday's constant. So hopefully again you appreciate that, the fact that when we report these constants in these types of equations, that they are coming from the slope of this relationship. And so if we take the negative of the slope, right, this is a negative slope, and so if we take the negative of that, it would give us then a positive Faraday's constant. So this ends up being 96,500 coulombs per mole of electrons. So this is the electric charge that we would observe for 1 mole of electrons. So it just basically comes from plotting then the free energy of a reaction versus its cell potential. And then of course it ends up being that the numbers of moles of electrons will dictate this relationship. And you can imagine the more moles of electrons that are being transferred in the reaction, that ought to impact the slope of that relationship. So just to give you a little bit of quick background on what this relationship is, why it hopefully kind of makes sense that positive cell potentials should give us negative delta G's and vice versa. Okay, so what we want to do now is think about, well, what if we have non-standard conditions in our reaction? What would the cell potentials look like? And so hopefully you can recall back to our equilibrium chapter, where we came up with this idea of delta G at non-standard conditions is simply equal to the standard state delta G plus RT natural log Q. And hopefully you remember from that chapter that we said that standard state pressures equal 1 atm, concentrations equal 1 molar. And of course, because we're working with electrochemical reactions, usually everything's in concentrations, except of course if we have our hydrogen electrode where we have 1 atm pressure of hydrogen. But if everything's in the standard state, then Q equals 1. And then of course delta G is simply equal to delta G naught, right? So we know that standard state, we're at delta G naught. And then our other condition that we had was that if we're at equilibrium, we know then of course that delta G equals 0. There's no change in the reaction, so this delta G ought to not be changing, it ought to be 0. And then of course Q equals K. Just a quick review of our non-standard state delta G. So we can use this equation now with our cell potentials. So on our previous slide, we learned that delta G is minus NFE, and of course delta G naught is minus NFE naught. So we can plug those values in to this delta G equation, and we rearrange the constant NF and combine it with RT. We can then find that E equals E naught minus RT over NF times natural log of Q. Now when we do cell potentials, it's a convention to use log base 10. So to convert natural log to log base 10, we use this 2.303 factor. And so we then just combine that with our constants. So E equals E naught minus 2.303 RT over NF, now times log base 10 of Q. And now we can combine our Faraday's constant, our gas constant expressed as joules per mole Kelvin, and we'll just use a standard temperature of 25 degrees Celsius. And if we combine all of those terms, that gives us 0.0592 volts. So when we combine coulombs per mole of electron with joules per mole K, that ends up giving us a volt unit. And of course we still have N, which is our number of moles of electrons, which will be involved in the redox reaction. So again here, this is what we call the Nernst equation. So this was developed by a scientist named Nernst. And it gives us kind of a similar way to deal with non-standard state that we had with our delta G. And so again, if we're at standard state, which of course is where everything is 1 molar or 1 atm if it's a gas, then we know that Q equals 1 and E equals E naught. All right, so there's not going to be any difference in our non-standard cell potential and standard cell potential. And then of course, if we're at equilibrium, then we know that the E cell equals 0. So this non-standard cell potential would be 0 because we're no longer now differing from our equilibrium state. There's no change. There's no change in the potential. That basically tells us that the battery or the galvanic cell has run out, right? We've reached a state. So equilibrium for a battery or a cell, galvanic cell, is basically there's no more change. The reactants have depleted. That's the equilibrium state. So there's no potential. And then, of course, if we're at this equilibrium, Q equals K. Okay, so very similar way to treat these non-standard cell potentials as we dealt with them with delta G, free energies of reactions. Okay, so hopefully that gives you a little bit of overview of where this Nernst equation comes from. The key thing is that we're relating delta G to cell potential, like we saw in the previous slide, and now we're just plugging this relationship into our non-standard delta G equation that we developed in our equilibrium chapter. Okay, so how would this work? So I wanted to do an example of how we would use the Nernst equation with a problem. And so, so there's the Nernst equation again. And we're going to generally be doing these at 25 Celsius. So this is assuming we're at standard temperature, 298 Kelvin, because that's how we derive this 0.0592 constant. And let's just do an example where we are now using a cell. So here we have a galvanic cell where we have a copper 2 iron 3 cell, and we're undergoing a change between iron 2 and iron 3, and copper 0 and copper 2. And we have now a cell where we have these observed concentrations. Let's say we start with these concentrations of ions that we put in our cell. And so we can then determine what is the non-standard cell potential of this galvanic cell using our Nernst equation. Now, of course, the first thing we need to do is just determine what are our half reactions. So we can say we have copper 0 here in our reaction. It's converting to copper 2. So we know that that must be our oxidation. The copper gave up electrons. So we have 2 electrons that are given off. If you look on your standard cell potential table that we worked on in lecture previously, well, actually, I'm not going to call that reduction. I'm just going to call it E naught, E cell, E half cell. Because now we have the oxidation. So the reduction in our table is positive 0.34 volts. So this oxidation would be negative 0.34 volts if you look at your cell potential table. And then we can see that iron is reduced. So we have iron 3 being reduced to iron 2. Remember, this is aqueous. That's also aqueous. And of course, because we have 2 moles of electrons being given off by copper, we need to multiply that entire reaction by 2 to make the electrons balance. But of course, remember, when we multiply the reaction by some coefficient, we don't change the cell potential. Remember, the cell potential is a property that's just a potential energy difference. It's not dependent upon how many moles of that reaction we do. So if you look on our standard reduction potential table, the iron 3 to iron 2 reduction is positive 0.77 volts. So if we add these together, the E cell for this reaction is positive 0.43 volts. So that's our standard cell potential for this reaction. Okay, so now let's use our Nernst equation to figure out what's the potential of this cell at these concentrations, non-standard state. So just to rewrite the Nernst. Okay, so we know that our E cell is positive 0.43 volts. Our N, our number of moles of electrons, is 2. 2 electrons were exchanged, so we can plug in that. And our Q, remember, Q is products over reactants, very similar to K. So we have iron 2, which is 0.2 moles, 0.2 molar. And we have to square that because of the mole coefficient. And we have copper 2, which has a mole coefficient of 1, concentration of 0.25. And then we're going to divide by reactants. So we can ignore copper because it's a pure solid. So we only have iron 3, which is this concentration. And again, we have to square that concentration. So we do that. So if we take the log of that expression and do our math, we'll find that E equals positive 0.25 volts. So we could see then that we're not at standard conditions. So now the question is, why was our voltage lower compared to our standard cell potential? So hopefully we can figure that out by looking at our Q. We can see that the concentrations of products was higher than our concentration of reactants. Right, so we had 0.2 molar, 0.25 molar for our products, but this 1 times 10 to the minus 4th molar for our reactants. So fairly significant increase concentration of products. So now we know that if Q is bigger, this is our standard state. Q equals 1, we can see then that we have now a Q that's greater than 1. So that's going to then shift the reaction towards reactants. So we know then that must be answer choice C. And hopefully this makes sense. If the reaction shifts towards reactants, right, that means that we have a less spontaneous reaction. And of course, if we have a less spontaneous reaction, that means we have a less positive cell potential. Just as we would have a less negative free energy, we would have a less positive cell potential. So by having these higher concentrations of products versus reactants, we then get a cell potential that's lower, less positive than our normal standard cell. So hopefully you can see then the usefulness of the Nernst equation. It helps us predict where our cell potential would be relative to this standard cell potential. Okay, so I hope that helps. Give you a little bit of a review of how the Nernst equation works. And then you're gonna have an online quiz where you can go practice this. So, reference this video as much as you need to as you work on that online quiz and where you get to practice the Nernst equation. Okay, and we'll see you next time.